And so we're going to start talking about maximum power transfer now. So if you have a circuit that looks like this, so here's the generator. So this is the internal impedance of the generator. So that's this whole thing. And it's normalized to 1, so let's say it's 1 ohm. Then if you attach a load to this generator and you change the resistance of the load from 0.1 to 10, you will see that the maximum power occurs when RL is equal to RS. And you can see the derivation of equations over here that, can show you the same thing as the graph. So that means that there's an optimal condition for the load impedance when you attach it to the generator. So if the generator impedance is 1, the optimal load is 1. If the generator impedance is 50, the optimal load is 50. If the generator's impedance is a complex number, then these equations become a little more complicated, but you can also show that the load impedance has to be what? Let's say this is ZL. What does load impedance have to be? Conjugate. Right, complex conjugate. So when you have a complex conjugate load, then you will see that you have the maximum power transfer. So in other words, when we have a complex impedance of the generator and the load, then these two have to be complex conjugate of each other, which means that the real parts have to be the same and imaginary parts have to be, so this one has to be a negative of the generator's impedance. So what is it that we're doing when we're making a matching circuit? If this is the generator and this is the load, inserting this impedance matching circuit, make this load impedance look like ZG conjugate, and it will make the generator and the circuit look like ZL conjugate. So both load and the generator will see complex conjugate of each other. Okay. So let's see simplest impedance matching case. So we will be able to design a lumped element impedance matching network for the load impedance 1 plus JX or 1 minus JX. These are normalized values already. So we want just to remove the reactance because we want to make the load impedance equal to the generator impedance, which normalized value is 1. So the load impedance is given, 50 plus J50. Find the impedance matching network to match this impedance to 50 ohm generator, right? So how do we do that? Well, first, we normalize the impedance because we want to see where is it on the Smith chart, right? So 50 plus J50 divided by 50 is 1 plus J1. So where it is, so what we're going to now observe is we're going to observe how this looks on the Smith chart, how does it look in terms of the circuit and what we're actually doing, right? So the goal of impedance matching exercise is to start, in this case we are on this 1 plus J1 point, which is somewhere over here. The goal is wherever that dot is on the Smith chart, to move it to the center. So we want to move it from where it is to the center. We can only use the circles that are centered on the x-axis. And the reason for that is when we are moving on these circles that are centered on the x-axis, on these circles the resistance or conductance is constant. So we don't have to add capacitance. We don't have to add resistors. We only add capacitors or inductors. The reason why we don't want to add resistors is because these resistors will take up the generator's power, and we don't want that. We want all the generator power to go to the load. So we just want to use capacitors and inductors. Okay, so as far as the circuit goes, we have 1 plus J1, which would be a resistor in series with a inductor, and on the other side we have a generator. So what do we have to insert here to see the complex conjugate of the generator, which is 1. So what do we have to add to this so that we see, looking from here, the impedance Zn of 1? A capacitor in series. So why is that? Why do we have to add a capacitor in series? Because you see, if you look at the equation for this impedance, it's 1 plus J1. Right? So for us to only have 1 over here, we have to add minus J1, right? Then this and this cancels, and the input impedance is just 1, right? So the input impedance, looking from here, is R plus J1, and then you add minus J1 over here. Now, why are we adding this in series? We're adding this in series because when we add this element in series, we can just add these 3 impedances, right? Because impedances add in series. So we add this in series, then we can just cancel these 2. They cancel, and the only thing we're left with is 1. Okay, so on the Smith chart, the way that looks is 1 plus J1 is over here. This is R equals 1 circle. When we add minus J1, we go to the bottom of the circle. So here is 1 plus J1. This is where Zn is 1. If we add minus J1 to this Z, we get matched impedance. So here is that initial impedance, 1 plus J1. We add minus J1 in series. The total input impedance, which is over here, is just 1. Okay, so let's see if you can do this. So find the impedance matching network to match impedance 50 minus J100 to 50 on generator. Describe how is the load impedance transformed using Smith chart, and then sketch the circuit. Load impedance, the impedance matching circuit, and the generator. Like the Smith chart. Show me on the Smith chart how that looks. Yeah. So here's what you should have on the paper. Here's the load impedance 1 minus J2. You have to add plus J2 to ZL to get the impedance of 1, right? So what is that? First, there's a couple of questions. The first question is, what is this Z is equal to plus J2? What kind of element is that? It's an inductor because plus J2 means plus J omega L. So that's an inductor, right? So and then why is it in series? It is in series with this because we're adding 2 impedances. When you add 2 impedances, the elements are in series. So if you look from this direction, you see that the input impedance is 1 plus and minus J2 cancel, so it's just 1. If you look from the output, from the load side, you see that the impedance is 1 plus J2, which is a complex conjugate of the load, right?